Probably at some point in your life, you've played a game of chance where you have a chance to win something. Maybe there's even a cost associated with the game. We want to figure out what makes these games fair. And we're going to use expected value to do it. So in a game of chance, the game is considered fair when the expected value is equal to 0. So that means if you play many, many times, you're going to win an average of $0 per game. So neither the house nor the player is walking away with money. But few games of chance really are fair, right? Because in a carnival, in the long run, aren't they out to win money? It's how you can keep playing. So we're going to do a process where we define our random variable, make our probability model, and then calculate the expected value. So we're going to start kind of simple here. It says throw a die. If you win $2 when the number is even and you lose $1 when the number is odd, what's the expected value? And then if you pay $1 to play the game, will you win in the long run? So remember, we use a capital letter to define our random variable. So I'm going to say X is the amount of money you will win. So now we're going to make our probability model. And I always want 2 rows as we do this. And you are going to put the values your random variable could take on. So it says you could win $2 or you could lose $1. So I'm going to say that's negative $1 if you're losing. And I don't see anything else described. So my second row is going to be the probability of this occurring. So if I'm tossing a die, I'm going to get an even number 3 out of 6, or 1/2 of the time. And then I would get an odd half the time as well. Remember, what makes this probability distribution valid is all values are between 0 and 1 for the probabilities, and they sum to 1. So now we're going to calculate the expected value. Remember that is just taking the random variable times a chance, plus the next one times a chance, and you repeat that. So our expected value is 2 times 1/2 plus negative 1, or even minus 1 times 1/2 would be the same as plus negative 1. If you toss that into your calculator, you're going to get 0.5 or 50 cents, and that's a positive 50 cents. So is this game fair? Well, in order to answer that, we have to look at the cost. Presently, what this means is if you play many, many times, you can expect to win, because it's positive, an average of 50 cents per game. But to get the true expected value, we need to subtract the cost of playing. So I need to subtract $1 here to get an answer of, it has an expected value of negative 50 cents. So since my expected value is not 0, this would not be fair. So it's no, if you play many, many times, not just once, you can expect to lose, because it's negative, an average of 50 cents per game. So remember, you could never actually lose 50 cents if you play just once. You're either winning 2 or losing $1. And that's, of course, after you've paid $1. But this is an average over a long period of time. Here's a second scenario. A casino game costs $3.50 to play. You draw 1 card from a deck. If it's a heart, you lose $10, whereas if it's the queen of hearts, you win $50. Is this a fair game? So again, let's define our random variable. I'm going to say it's the amount you win. And now I'm going to define my probability model. So I need each amount you win and the chance of it occurring. So I see the greatest is 50. Could win 10. And I also need to consider, it's not explicitly said, but kind of implied here, because if I'm drawing from a card from a deck, it's only talking about the hearts. Well, there's other cards in the deck, so I'm assuming that must mean that I don't win anything if I draw from that card, or one of those cards from the deck. So let's think about what's in a deck of cards. There are 13 cards in a deck of each suit, for a grand total of 52 cards, and we've got hearts, diamonds, clubs, and spades. Okay. So starting with $50, you win that with a queen of hearts. So there is only 1 queen of heart in the deck, so that's going to be 1 out of 52. If it's a heart, you win $10, so that would be everything except the queen of hearts. So that would mean there's a remaining 12 hearts out of 52. And I could reduce that, but I'm just going to leave it like that. So then 0 would be everything that's not a heart. So that is the other 39 cards, or 3/4 of the deck. So I could do 3/4, or leaving it as 39 out of 52, which, all right. Again, valid probability model, because these are going to sum to 52 out of 52, which is 1, and they're all between 0 and 1. To get my expected value, I'm taking the random variable times the chance. Next one, plus 0 times 3/4. So I toss that in the calculator, and I get $3.27 for my expected value, but there was a cost to play, so I need to subtract that cost from my expected value, or I should say that's included in the expected value. So I'm going to subtract the 350, and that gives me a final answer of negative 23 cents. So is it fair? No, my overall expected value is not 0. You're expected to lose an average of 23 cents per game if you play many, many times. So let's say at Spring Fling, the math department designs a dice game. Learners must roll 2 dice and record the sum. If you roll a 2, 3, 4, 10, 11, or 12, you win $5. If you roll a sum of 5, 6, 7, 8, or 9, you lose $3. Find the expected value for learners per game. Okay, so let's define our random variable. So it's the amount a learner wins per game. So I'm going to start setting up my probability model. So you're winning $5, or there's no cost to pay, but you could lose $3. So you better have $3 in your pocket. And we need to figure out these probabilities, and it's talking about rolling 2 dice and calculating the sum. So if I just list out what I could possibly get when I'm adding 2 rolls together. So if I rolled a 1 and a 1, that would sum to a 2. Switch colors here. A rolling 2 and a 1 would sum to a 3. And if I just go down this, it's just going to be increasing by 1 each time. If I roll a 2 and a 1, next column, that's a 3. 2 and a 2 is a 4. 5, 6, 7, 8. 3 and a 1 is a 4. 3 and a 2 is a 5. Going down 6, 7, 8, 9. And I'm going to finish filling in this chart. So I finished my chart all the way down to I could roll a 6 and a 6 to get a sum of 12. So how many different outcomes are there? There are 36 in here, right? 6 on one, 6 on the other. 6 times 6 gives you 36. So how do I win $5? It tells me getting a sum of 2, 3, or 4. So I'm going to highlight those sums. So it's 2, 3, or 4. That's these here. Or 10, 11, 12. So that's these ones down in this corner. So if I add those up, that is a total of 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 36. Or a third, which would mean the remaining would be 2/3. So if you wanted to sit here and add up these, yep, you're going to get 24 out of 36, which reduces to 2/3. All right, calculate your expected value, which is going to be each random variable times the chance of it occurring. So 5 times a third minus or plus -3, if that makes more sense to you, times 2/3. There's no cost in this one, so if I just toss that in my calculator, I'm going to get negative 33 cents per game. So again, if we play this many, many times, learners can expect to lose an average of 33 cents per game. Remember, in no particular game could you lose 33 cents. You either gain 5 or lose 3. But if you do this over a long period of time, right? So imagine you play 10 times. If you play 10 times, you would multiply this by 10 times 33 cents. You could expect to lose overall $3.30 or $3.33 if you take it out to another decimal place. See if you can set up this next one. Hit play when you're ready to check your answer. A player rolls a die and receives the number of dollars equal to the number on the die, except when the die shows a 6. If a 6 is rolled, the player loses $6. If the game is to be fair, what should be the cost to play? So if I let X be the amount you win when you play, I'm going to set up my probability model. So you're winning either $1, 2, 3, 4, 5, or losing 6. And the chance of this happening is going to be 1/6 because each side of a die is equally likely to pop up. So then you're going to calculate your expected value, which would be as you see on the screen. And when you toss that in your calculator, you get $1.50. So currently, the way it is, if somebody's playing this game, overall, you can expect to win an average of $1.50 per game they play. So you need to charge something, especially if you're designing this. If you want this game to be fair, you would charge exactly $1.50, which would mean everybody breaks even in the long run. If you wanted to make a profit, you would charge more than $1.50.